Hi everyone and welcome back to Data Science with Marco. Today we're picking up from the last video where we built our baseline model, and now we will try to run multiple models to get some better results. So let's get started. So we know that a good way to improve on linear regression is to use something called regularization. So this is exactly what we are going to do. We will first try ridge regression and later we will try lasso. So let's get started right away with ridge regression. So I'll just write it out. Multiple linear regression with regularization, and in parentheses we'll use ridge regression at first. So we'll initialize the model. Ridge will be equal to ridge. And now we will do some cross-validation to optimize the regularization parameter. So in this case, the parameter is called alpha, and we will set different values for the model to try out. So 1e to the minus 15, to the minus 10, to the minus 8, to the minus 4, sorry. And then we'll do 1e to the minus 3, 1e to the minus 2, and we'll try 1, 5, 10, and 20. Perfect. Now we will initialize our grid search. So ridge regressor will be equal to grid search CV. We pass in our model, then we pass in the parameters to try out. We need to pass in a scoring. So and in this case, we'll use the negative root mean squared error. And finally, we will do 5-folds cross-validation, so CV will be equal to 5. Once this is done, we will fit the model. So we write ridge regressor dot fit, and we fit on X train and Y train. And once that is done, we can find what are the best parameters, or in this case, the only one parameter alpha, with the method best params underscore at the end. Don't forget about it. And we can also print the best score by writing print ridge regressor. And actually, don't forget to put the negative here because we are using the negative root mean squared error. So we want to bring it back to a positive dot best score and underscore at the end. Now we did not import our libraries to run this cell just yet. So let's go back up. And we do our necessary imports here. So from sklearn.model selection, I will also import grid search CV. And from linear model, sklearn.linear model, I will import ridge. Awesome. Run this cell and we can go back down to our last cell and run this code. This takes a little while, and as you can see, we get that the best parameter is actually alpha being equal to 1. So now we can actually use this parameter to retrain a model specifying the value for alpha and then get our validation and test root mean squared error. So we reinitialize the model and we specify alpha equal to 1, and then we fit it to X train and Y train. Then we can get some predictions. So ridge reg pred is equal to ridge reg dot predict, and we predict on X test. Now that we have those predictions, we can calculate the test RMSE. So test RMSE will be equal to the mean squared error. We pass in Y test and we pass in our predictions. Finally, don't forget to put the squared equal false so that you actually get the root mean squared error. And then you can print it out. So test RMSE will be equal to our variable test RMSE. Perfect. Now to get the validation RMSE, this will be very similar to what we have done just above. So first we need to predict on the validation set. So ridge reg pred val will be equal to predict on X underscore val, and then you can calculate the RMSE. So as above, mean squared error. In this case, we pass in Y from validation, pass in the predictions on validation set, and squared is equal to false. Finally, we'll print it out. So print, and validation RMSE is our variable var RMSE. Once you run this cell, you get 1.564, which is a slightly better score actually than our baseline model, which is just a linear regression, 1.5661. So this is good. We are on the right track. Actually, regularization did help in this case. So now let's try the other regularization for linear regression, which is Lasso. So again, multiple linear regression with regularization. And in this time, in parentheses, we'll write Lasso. Now let's go back up to our import cell, and we will import the library for Lasso. So right under ridge from sklearn.linear model, let's import Lasso. Awesome. Run this cell, and you can go back down. So from now on, you can try to pause the video and try it on your own, because the code will be very similar to what we have done with ridge regression, only this time we're using Lasso. So actually, I'm simply going to copy paste the parameters from above and paste them under, because we are going to try the same set of values for alpha here for the Lasso algorithm. And then just like above, grid search CV, pass in Lasso the parameters. The scoring will be the same, so neg mean squared error, and the cross validation again will use 5 folds. Finally, we can fit Lasso regressor on X train and Y train, and like above, we'll be able to print the best parameters. So print Lasso regressor dot best underscore params underscore, and then print the negative of Lasso regressor dot best underscore score underscore. Now I am getting a mistake here that Lasso is not defined. It's probably because I forgot to run the cell above. I'm sorry about that, guys. So make sure you run this cell whenever you import a new library. So now that I run it, I can rerun this cell here. And after a while, we get that the best value for alpha is 0.01. So just like with regression, I'm going to use this value now to fit the model again and get our test and validation RMSE. So Lasso reg will be equal to Lasso, and in this time we specify that alpha is equal to 0.01, as this was our best parameter from grid search. And then we fit it on the train set, so X train and Y train. Now, as we have done before, we need to get our predictions. So Lasso reg pred is going to be Lasso reg.predict on X test. And now we're ready to calculate our test and validation RMSE. So actually, I'm just going to grab this code that we have above, paste it down here, and we'll just change the name of the variables so that they fit for Lasso. So instead of ridge reg, it's going to be Lasso reg pred. And here, instead of ridge, I'm going to write Lasso as well. Here as well, it's not ridge, it's going to be Lasso reg. And finally, for the val RMSE, we pass in Lasso reg pred val. So if everything was done correctly, which I think it is, you should get the following. So 1.5564 approximately, which is a little bit higher actually than ridge regression. So now that we have tried everything about linear regression, I actually want to try some tree-based model. So we'll explore some decision trees, mainly random forest, and probably bagging as well. So before moving on, we are actually going to change the features that we are using. So in this case, we will consider the sex of the abalone as well. So we need to redefine our training set and validation set. So here X will be equal to the training set, and then we're going to drop every single column except height, weight, and the sex. So you drop rings, diameter, hole weight, drop shocked weight, And then we will also drop, let me move on to the next line for you guys so you can see the entire code without having me to scroll. So we will pass in viscera weight and also the shell weight. And that should be it. And we'll drop along the axis equal to 1, so we drop the columns in this case. And then y will be equal to the training set, and we only want the column called rings, dot values, dot reshape, -1, 1. Perfect. And now we will do the same thing, but for the validation set. So xval will be equal to the validation set, and we're going to drop the same columns as above. So let me just grab this piece of code right here, paste it down because it's going to be the exact same columns that we're dropping. And then for y val, again, it's going to be the validation set, and we want the column rings dot values dot reshape -1, 1. Awesome. Now we are going to redefine our train and test set. So x train, y train, x test, wait, actually no, it is x train, x test, y train, y test will be equal to the train test split. And then we pass in x, we pass in y, and then the test size will be again 10% of the entire training set. And we'll set the random state equal to 42 so that every time we run this code, we'll get the same split. So before actually moving on, we will import our libraries necessary for random forest and bagging. So let's go back up. And then after linear model, so from sklearn.ensemble, let's import random forest regressor because it is a regression problem. We're trying to predict a continuous value. And from sklearn.ensemble, we'll also import bagging regressor. Awesome. Make sure that you run this cell because we have imported new libraries, and we can go back down and try out random forest. So again, we will use some grid search to optimize some hyperparameters. So RF is going to be random forest regressor. No, actually here I do not want to specify the number of estimators. This is something that we will find out after when the grid search is complete. So sorry about that. Only a random forest regressor with all the basic parameters. And then the parameters that we want to try in this case is, well, you guessed it, the number of parameters, the number of estimators, sorry, so n estimators. And now we'll say that we want an integer of x for x in np.linspace 100 to 1000 with steps of 10. So what this creates is an array from a 100 to 1000 with steps of 10, so 100, 110, 120, etc. And we will try every single value here as the number of estimators in our random forest regressor. So now we can start. So RF regressor is equal to grid search CV, pass in the model, pass in the parameters. The scoring again is neg mean squared error, and we'll do 5-fold cross validation. And then we can print our best parameters, just like above. And of course, we can print the best score. So negative RF regressor dot best score. Now this should be RF. And my other mistake here is, right, so I did not fit the model on anything, so that's why we cannot have the best params and the best score. So sorry about that, guys. Make sure that you fit your model on the train set before you call this. And of course, ytrain.rabel, because we're doing decision trees. So this is going to take a while before the grid search is over. So you can pause the video and we will come back once this is done. Alright, so this took approximately 5 minutes on my end, and we get that the optimal number of estimators is 300. So again, we can use that information to train our model and get the validation and test RMSE. So we redefine the model, and this time we specify the number of estimators to be equal to 300. and then we fit it on the train set. Perfect. Now we are ready to calculate our test RMSE. So for that, first we will get our predictions. So rf_reg_pred will be equal to rf_reg.predict x test, and then the test RMSE is the mean squared error, pass in y test, pass in the predictions, and again squared is equal to false. Nothing new up until now. And finally we print it out so that we can check our values. Test RMSE is the variable test RMSE. Then we can get the validation RMSE. So first we predict on the validation set. So rf_reg_pred_val is equal to rf_reg.predict, and we predict on x val. Then the validation RMSE, very simple, mean squared error. We pass in y val, and the predictions on the validation set, so rf_reg_pred_val, and squared is equal to false. Finally, we print it out. So f, and then the validation RMSE is the variable val RMSE. Run this cell, and again, I did not write rf here, sorry about that. And I forgot to use ravel on my predictions. Again, sorry about this mistake, guys. So once we run that and everything is good, you should get the following value, 2.22. So this is actually worse than our baseline model, and again, worse than multiple linear regression with regularization. So this is actually an interesting result. Let's see if we get something different by using bagging. So again, you can pause the video and try it on your own because we will do something very similar, although with a little twist in this case. So bagging regressor, and now we will optimize two parameters. So we'll optimize the number of estimators, and this time we'll try a larger array of values. So np.linspace, and we'll go from 10 to 1000 with steps of 10. And we will also optimize the max samples parameter. And similar to what we have done with n estimators, in this case, we're going to take the float of x. For x in np.arrange from 0.1 to 1.1 with steps of 0.1. So this will generate an array going from 0.1 to 1 actually with steps of 0.1. And we will do a grid search using the combinations of these two parameters. So it will try every possible combination of those two parameters. So you can imagine that this is going to take a while. So again, pass in the model parameters, the scoring, and we'll do 5 folds cross-validation. Then you fit X-train and Y-train. And then we will be ready to print out our best parameter combination, and of course our best score. Running this cell, and I forgot to use ravel again, so make sure that you do ytrain.ravel. all right, rerunning this cell. Now like I said, this will take a long time, so in my case it took 15 minutes, so I will come back once this is finished. On your end, you can either run it on your own, like I said, it will take approximately 15 to 20 minutes, or skip completely this part and simply run the model once we get the optimal values. Alright, and it is done, like I said, after a good 20 minutes, and we get that max sample should be 0.1, and the number of estimators should be 670. So let's run our model with those parameters set. So our BG reg is going to be equal bagging regressor, and then we specify the two parameters. So number of estimators is 670, and the max samples will be equal to 0.1. Perfect. So just like we have done above, we then fit the model on X-train and Y-train. .ravel, this time I'm not forgetting. And now let's just grab this piece of code here for the RMSE and paste it down. so that we avoid too much repetition, guys. So let's just write this comment here, test RMSE. And of course, we need to predict before we can calculate any error. So bgreg pred will be equal to bgreg.predict on xtrain. Perfect. And now let's just replace the variables. So it's not rf, it's bg. Here it's not rf, bg. Replace this as well with bg and this with bg. Everything should be good. And again, my mistake here was that I predicted on the train set and not the test one. Sorry about that. So once that you run this cell, you get 1.746. So it is better than random forest, but not as good as our linear regression models like Lasso or ridge regression. So at this point, I think that we should try maybe some state-of-the-art library, and so we'll use LightGBM. So again, you need to go back up and import LightGBM. So import LightGBM as LGB. Now, of course, this is not a standard library that comes with Anaconda, so you will have to do a quick Google search to install it. So very simple. If you search on Google for LightGBM Anaconda, you should get the first result here on the top. And then you have the instructions right here. So conda install -c conda forge LightGBM. And then if you open your Anaconda prompt, you can simply paste it there and press enter to install it. Now I'm not going to do it because I installed it already. So LightGBM is actually a decision tree library as well, open source from Microsoft, and it was used in many winning algorithms in different competitions. So really the performance of this algorithm is amazing. So let's try it out for our problem. So for the parameters, we will only set the learning rate in this case to 0.01. And then you actually need to pass in the data set in the format that LightGBM can understand. So train data will be lgb.dataset, pass in xtrain.values, and the label is ytrain.ravel. And then you can, so actually here I did not write this correctly. So it shouldn't be LGB pred, it should be LGB reg. Sorry about that. So the regressor, and then it's just, you can train it and you pass in the parameters, the train data, and 100 is the number of rounds it will do. Then you can do the predictions and you simply, with the method predict on xtest, and now we can calculate our RMSE. So test RMSE is equal to mean squared error, pass in ytest, pass in our predictions from LightGBM. So LGB reg pred, and squared is equal to false. Then we can print it out with our template literal. So F is test RMSE, and you pass in the variable test RMSE. Perfect. And finally, validation RMSE. So first we need to predict on the validation set. So LGB reg pred val is equal to LGB reg dot predict x validation, and then the validation RMSE is mean squared error, pass in y val, the LGB reg pred val, and squared is equal to false. Then we print it out. So F, and then the validation RMSE is the variable val RMSE. Awesome. And we get the best score of all models, so 1.5097. So this is perfect. At this point, we will consider this as the winning model. So now let's just compile the results so we can show it in a data frame, and it's going to be sorted by the values. So first we need to define a dictionary that will contain the data. So I call it RMSE compilation, and then we'll define all the models that we tried. So we tried linear regression. We also tried ridge regression, we did lasso, then we did random forest, then we also did bagging, right? And finally we used LightGBM. Awesome. And then now that our models are defined, we will simply compile the RMSE values that we got. So RMSE will be equal to, and then you can go back up and write it out. I'll just write it down here for you guys. So 1.5641 for linear regression, or actually 56.62. Then for ridge, we got 5641, then 5564, and then 2.2334. The same for bagging, and then for LightGBM, we got 1.5097. Awesome. Then I will simply create a data frame from this data. So RMSE df is going to be equal to pd.dataframe, and then we pass in to the parameter data RMSE compilation. And now we will simply sort the data frame by RMSE. So dot sort underscore values by RMSE, and we want ascending to be true because the lowest RMSE is the best score. And as you can see, we get that LightGBM is our winning model. All right, so that was quite a project. Congratulations on making it to the end. Now, I would like to give you some hints as to how you can make this project your own. So an example that you could do is maybe write a function to avoid repetitive code. So we were copy pasting a lot of code for the RMSE. So maybe try to write a function so that we don't have to do that. Also, you could try to optimize other parameters or use different algorithms from those that we use in this project. And also, grid search CV was pretty long actually when we tried bagging. So like I said, 15-20 minutes. So maybe you can try to use randomized search CV, which is faster, but maybe will give better or worse results. Anyway, you should try it out, make experiments, and really take this project and make it your own. See you on the next one, guys.